second order system, right? And what is the general form of a second order system? Transfer function of second order system? Yeah, fine. So where omega n is the natural frequency of oscillation and the zeta is the damping ratio. And we have seen that the factor zeta is an important factor which predicts the characteristics of the system, right? And we have seen 4 cases. And in order to become the system to be in stable state, the value of zeta and omega n must be greater than 0. Then only our pulse lies in the LSP of the S-plane, right? And first case, when zeta is less than 1, that's between 0 and 1, we have observed that the nature of the poles are distinct, but having negative real part and imaginary part. That kind of system is said to be underdamped system. When zeta equal to 1, the poles are equal and have negative real part. That kind of system is called critically damped system. If zeta is greater than 1, poles are distinct and real. There is no imaginary part, and that kind of system is called overdamped system. If zeta equal to 0, poles are purely imaginary, and that kind of systems are called undamped system, right? And what is zeta? Zeta means damping ratio. It indicates the amount of damping put in the system, right? And omega n is the frequency at which the system response oscillates if there is an initial perturbation as input. And today we will see all the cases separately. So first we will take case 1. Case 1 is underdamped system. The zeta lies between 0 and 1. Okay, now for an underdamped system, what is the pole? It is minus zeta omega n plus or minus j omega d, right? Yesterday we have seen this. We have introduced one more time omega d. Omega d is the damped natural frequency, damped frequency of oscillation, where omega d is equal to omega n multiplied by 1 minus zeta square, right? So if we plot the pole location, this real part and the imaginary part, we have 2 poles located at this point and this point. We cut the negative real axis at some point. This is minus zeta omega n. This is the origin. This is plus j omega d. This is minus j Okay. Now, what we can see, what is the unit step response of the system? Unit step response. So what will be the unit step response? For that, first of all, we can write the transfer function y of s equal to u of s multiplied by the standard form is omega n square divided by s square plus 2 zeta omega n s plus omega n square. And for unit step input, u of s equal to 1 by s. So we can write y of s is equal to omega n square divided by s multiplied by s square plus 2 zeta omega n plus omega n square. So applying partial fraction, we can write a by s plus, and the next part we can write it as bs plus z divided by s square plus 2 zeta omega n plus omega n square. Okay, please find what are the values of the residues a, b, and c, and tell me. Okay, what about c? Minus 2 zeta omega, right? So we can write y of s is equal to 1 by s minus, I can take it out, so minus s plus 2 zeta omega n divided by s square plus 2 zeta omega n plus omega n square, right? So in order to how to solve this, so we can do some mathematical analysis here, and we can convert this part into some non general equations form, right? So that what I'm doing is I'm to numerator part I'm writing as it is. So in denominator part, introducing 2 more times 2 zeta omega n, yes, plus I am adding and subtracting 2 times, that is omega n square zeta square minus omega n square zeta square plus omega n square. Okay, so you can write s plus 2 zeta omega n divided by, what about this one? This can be written as s plus zeta omega n the whole square, right? You can write like this. And what about the next part? What is this? Is omega n square minus omega n square zeta square, which can be written as, if you take omega n square out, it will be 1 minus zeta square. So what is this? Yeah, correct. omega d square. So we can write this as omega d square. Right. So this also we can split it, then it will become the standard form. So we can write 1 by s minus s plus zeta omega n, right, divided by s plus zeta omega n the whole square plus omega d square, right, minus one more zeta omega n is there, that you can, it is not z, yes, zeta omega divided by s plus zeta omega n the whole square plus omega d square, right. Yeah. So now it is in the standard form, right? Simply you can apply inverse Laplace transform and do it. So what are the things you can observe from here? And write Laplace inverse of e power minus at cos bt. What is it? This s plus a divided by s plus a the whole square plus b square. Similarly, Laplace inverse of e raised to minus at sin bt. How we can write is b divided by s plus a the whole square plus b square. So using this relation, you can find y of t. So y of t is Laplace inverse of the above equation. So 1 by s becomes 1. What about this one? This part will become e power minus zeta omega n t cos omega dt, right? And this other part becomes minus e power minus zeta omega n t into sin omega dt. So this will be the unit step response of an which system? Unit step response of an underdamped system. Stable linear time invariant underdamped system, right? So what are the observations? You have already seen this unit step response, right? And what are the observations from that? The exponents we have in this we have two exponential terms, right? And we already seen that the exponents of this exponential terms are real part of the poles, right? Is it coming correct? So for an underdamped system, the pole is minus zeta omega n plus or minus j omega d, right? So it is coming as the real part of the pole. So another observation is, what is the steady state value when t tends to infinity? What is the value? Y of t is 1. Yeah. And I already mentioned that the standard form is like this, right? Means d square y of t divided by dt square plus 2 zeta omega n y of t plus omega n square y of t is equal to omega n square to u of t, right? So why this omega n square is sitting along with u of t. Usually u of t only will be there. Why means since omega n square is present, we are getting the steady state value as 1. Otherwise, if this is equal to u of t, your steady state value will be y of infinity will be 1 by omega n square. So in order to make this steady state value unity, this omega n square is multiplied with the numerator. Okay, other than that, nothing is there in this. This you keep in mind. Okay. And any other observation? Here the steady state value is 1 and the exponents of the exponential terms are the real part of the poles. Any other observation? Yesterday we have introduced one more term, right? Omega d. So now we can define what is omega d. So we have two sine times, one sine time and cosine time. It is multiplied with the exponential time. And what is the frequency of that sine time? It is omega d. Omega d is called damped natural frequency. So how will you define omega d? Omega d is the frequency at which a damped second order system output is going to respond with respect to an input. That is the definition. Omega d is the frequency with which the damped second order system output is going to oscillate in the presence of an input. Clear? So you understood what is the difference between omega n and omega d. Okay. So how can we draw the response diagram with respect to t? We already know the equation, right? So how can we draw it? The response of the second order system. This is damped second order system. Let this be y of t and this is t. How can I draw this? We know the steady state value is 1. Let it be 1. What will happen to the waveform? Since the sinusoidal term is multiplied with the sine time, how the response will be? There will be a envelope of this in steady state. It will oscillate, but since it multiplied with the decaying time, what will happen? The oscillation will reduce. When t tends to 0, it will go to the steady state. Okay, so it will be like this. It will start from 0, slowly it will reach, but because of this sine time and exponential time, it will cross the steady state value, right? It will cross the steady state value, again it will come back, but when t tends to 0, these oscillations will decay because of the exponential time, right? And when t increases, finally it will reach some point. So this will be the response of the second order system, damped second order system. Okay, and this part you can see that here the output is going beyond the steady state value This is called overshoot of the system. Overshoot. Okay, from this we can extract some points and some technical specifications also. So next we will discuss about the time domain specifications of the damped second order system from this. Time domain specifications of damped second order system. The first one is rise time. Is denoted as T smaller. Rise time is defined as the time taken for the response to reach 100% of its final value for the first time. For the first time. So we move back to the response. So it is defined as the time taken by the response to reach the 100% of the steady state value first time. So since it is oscillating, you can see first it is crossing this point and there will be an overshoot. Again it is coming back. There will be an undershoot. Again it is going beyond. Right. So many times it is reaching the steady state. So peak rise time is defined as the time taken by the response from 0% to the 100% for the first time. So this is the rise time. Okay, now how will you obtain the relation for rise time? How will you find the rise time from the response? How can we find out? How will you find out? We know at time t equal to tr, what is the value of y of t? What is the value of y? That is, yeah, it is 1, right? So just equate the relation y of t to 1. So what is the relation of y of t? It is 1 minus e power minus zeta omega n t cos omega dt minus e power minus zeta omega n t sine omega dt. Any other factors there? Something is missing, right? What is relation? Have we did any mistake here? Yeah, correct. Yeah, here itself some parameters missing. So zeta omega n is missing, right? Now it's correct, right? Okay. By omega d. Here. Okay. Okay. Now multiplied by zeta omega n divided by omega d. And this, all right, time t equal to tr, which can be equated to 1, right? So we can rewrite this equation as one minus e power minus zeta omega n, t becomes tr, cos omega d tr. So if I take this out, I can write plus sine omega d tr, and what about this one? You can substitute omega d is equal to omega n into root of 1 minus zeta square, right? So omega n and omega n got cancelled. Finally, you will get zeta divided by root of 1 minus zeta square, correct, is equal to 1, right? Any doubt? Yeah. So 1 and 1 got cancelled. So we will get e power minus zeta omega n tr cos omega d tr plus zeta divided by root of 1 minus zeta square sine omega d tr is equal to 0. So how to solve this? So it is having two sections, right? One is e power minus zeta omega n tr. You can see whether e power minus zeta omega n tr is 0 at t equal to tr. Yeah, because why? At t equal to tr, your output response is just finite value, right? Tr is a finite value. It is not going to infinity, right? So we cannot tell it is 0. Because for a finite value of time tr, this part is not 0. So we can write the only other part will go to 0. So we can equate like this: cos omega d tr plus zeta divided by root of 1 minus zeta square sine omega d tr is equal to 0. Right? So from this we can, if we solve this, you will get tan omega d tr is equal to minus root of 1 minus zeta square divided by zeta, correct? So from this we can calculate tr is equal to 1 by omega d tan inverse minus root of 1 minus zeta square by zeta. Clear? And finally we'll get is equal to 1 by omega d. So tan inverse minus theta, how can we write? How can we write? Because I want tr in positive value. Time will be in positive value, right? So how can we write? Can I write like this? Pi minus theta, where theta is tan inverse root of 1 minus zeta square by zeta. Can I write like this? Yeah. So what is theta? We will see now. TR is equal to pi minus theta divided by omega d. So this is the relation. This you keep in mind. What is theta? We'll see. Now we'll move back to our diagram. This diagram. Now you draw one line from the origin to this point. So by Pythagorean theorem, this is omega d. This magnitude is zeta omega n. Let this angle be theta. Okay. What is the hypotenuse of this? Let this is O. Let this is A, B. How will you find cos theta? Yeah, one second. I'll redraw this way from here itself. That is better. So I have a triangle like this with base zeta omega n. Oh, sorry. It was it is. So I have a triangle like this. This be theta. This is zeta omega n. This is omega d. Let it be A, B, O. So what is cos theta? Zeta omega n dv square root of omega d square plus theta omega n all square. So if you solve this, what you will get? This becomes zeta omega n divided by what is omega d? Omega d square can be written as omega n square 1 minus theta square plus theta square omega n square. So if you solve this, you get again omega n divided by omega n square. Oh, here square root is there. Root of omega n square minus omega n square zeta square plus omega n square zeta square. So this and this you cancel. Finally you will get zeta omega n divided by omega n. So also we cancel put zeta. So you get cos theta equal to theta, right? So one more observation I want to tell from here. Suppose theta is increasing. We know cos theta equal to damping ratio, right? So this angle is increasing means damping will increase or decrease? Yeah, damping will decrease. If this angle is decreasing, zeta will increase. Right, that is observation. And when zeta equal to, see, if zeta is 0, our poles are at exact imaginary axis, right? That you can observe. So if I increase this theta, the zeta value also will change like this, right? Okay. Now we'll move to another time. So from this you can find sine theta also. Sine theta is, so this is omega n, right? So theta, sine theta can be written as omega n into root of 1 minus theta square. So this is equal to omega n into root of 1 minus theta square divided by hypotenuse, that is omega n. So sine theta becomes 1 minus zeta square. So from this you can find tan theta is equal to zeta divided by root of 1 minus zeta square. So if I know zeta, I can find out theta. So if I know theta and omega d, okay. Root of 1 minus zeta square by zeta. So if I know a damping ratio, I can calculate theta as well as omega d. So if I know all those things, I can calculate the rise time. Correct? Clear? Yeah. So we have another time, peak time. The second one is peak time. Is denoted as T suffix P. So how to define peak time? It is, peak time is the instant of time at which the output reaches the first peak of the overshoot. First peak of the overshoot. So it is the time instant at which output reaches the first peak of the overshoot. In this graph, how can we indicate the peak? It is the time at which, so this is the first peak of the overshoot, right? So this is called peak time, T, P, and here you can see this period, it is exceeding the steady state value, and this part is called overshoot. And next we will define it. First of all, we will see what is peak time. So we understood that at a time t equal to Tp, the output is maximum, right? So how will you find the Tp from the response? How will you find the Tp? Yeah. So first of all, you can see the first derivative of the system, right, and equate to 0. Okay. Then what you can do is, one of the method is, you find the pole at which the derivative, first derivative is 0, and you find the second derivative of the system, and substitute that pole value in the second order system and check whether it is less than 0 or greater than 0. If it is less than 0, the function is global maxima. If the the second order derivative is greater than 0 for that particular pole, it indicates the local minimum. So in our case, we need to check whether at what value of pole with the second derivative of the step response is less than 0. So then only we will get the global maximum of this particular function. So first we will find out the maximum value. Then we'll see. So how will you find the maximum value for the first derivative? First take the first derivative of the system, value of t, and equal to 0. You also do it and find the first derivative. So if you take the first derivative, how can we write like? It is 1 minus e power some multiplied by cos plus e power sometime multiplied with sine, right? So if you take the first derivative, derivative of 1 is 0. So remaining part we can write like this, minus of e power minus zeta omega nt multiplied by minus zeta omega into minus. So it will become plus first function cos omega dt plus first function into raised to zeta omega nt, derivative of the second. That becomes sine omega dt multiplied by omega d. Here also 1 minus is outside, so it will become plus, again plus. We can write here zeta omega n divided by root of 1 minus zeta square e power minus zeta omega nt sine omega dt minus zeta omega d divided by root of 1 minus zeta square e power minus zeta omega nt. Sine becomes cos omega dt. So now here one term will come, right? The square will come, right? Yeah. This is equal to 0. So if you solve this part, omega d, if you substitute omega d equal to omega n multiplied by 1 minus zeta square, 1 minus zeta, root 1 minus zeta square got cancelled, finally you will get minus zeta omega. So this portion got cancelled. Finally you will get e raised to minus zeta omega nt omega d plus zeta square omega n by root of 1 minus zeta square multiplied by sine omega dt is equal to 0. And how will you calculate the TP? Whether e power minus zeta omega nt will be 0. No, right? Because yeah, at a time t equal to TP, the t is finite value. Since t is finite, it will never go to 0. So this will be not equal to 0. And what about this? This also, it is a positive value, right? This also will never go to 0. The only thing is this part has to go to 0. So you can equate sine omega d t equal to 0. So from this we can write omega t is equal to n pi by omega d, where n equal to 1 comma 2 comma 3, etc., etc., etc. This part will be 0, right? Anyway, it is already 11:20. We will stop here and we will continue tomorrow.